Good afternoon, everybody. Welcome to Tuesday afternoon at Chem 170 with your host, me, Dr. White. Some of you are still taking the test, but I'm recording this so you can watch the recording on my YouTube channel. All right, game plan for this rest of the week. Today, I'm going to go through and continue with carbohydrates. Tomorrow, I will go through the fats and oils problem set and finish up with carbohydrates and start some new stuff. And then, actually not that much new stuff left. And then on Thursday, I will go through the carbohydrates problem set. And I'll also do my world famous review for the next test. And I'll do some practice problems for test number 4. Now, I'm not sure when I'll get to it. Either we'll do test number 3, I'll go through tomorrow, or I'll go through on Thursday. Matters how late I want to stay up tonight, being honest with you. All right, let's get to work. Now, yesterday, I talked about chiral objects and achiral objects. Chiral objects have a superimposable mirror. Chiral objects have a non-superimposable mirror image, and achiral have a superimposable mirror image. Now, thing I didn't do yesterday, which I should have, but I have today, I have models. If you notice, I have this model right here. Think of carbon in the center. Black, silver, yellow, red. And here's its mirror image. If you had a mirror, see how the yellow goes to yellow? If the mirror was right here, red to red, silver, silver, far away, black. And now, if I try and superimpose the silver on silver and black on black, oh no, the yellow and red don't match up. So if I do it like this, then the silver and black don't match up. So these are non-superimposable mirror images. So these are chiral molecules. Now, important concept for this class is a chiral carbon. And a chiral carbon has 4 different atoms, 4 different groups, or a combination of 4 different groups or atoms on it. Let's go to our, and here we have a chiral center, which I'll call a chiral carbon, because we're talking about organic chemistry. It's an atom carbon in a molecule that has 4 different groups tetrahedrally bonded to it. And when carbon is not in a double or triple bond, like this, it's tetrahedrally bonded. That's the, so let's have some fun with this. And the question is 3 points each, circle the chiral carbons in, and A we have here. Now, what's a chiral carbon? A carbon with 4 different groups, 4 different atoms, or a combination of 4 different groups or atoms. Now, if a carbon has 2 or more hydrogens, it can't be chiral. So immediately this is out, this is out, this is out. We're left with this carbon and this carbon. So what do? we say it's got a hydrogen hydroxy group, methyl, and I'll call all this R. So, and I can call the methyl R prime. Hydrogen hydroxyl R prime R, 4 different groups. And therefore, this is a chiral carbon. I got the hydrogen, but you know what I'm talking about. Now, let's clean up the picture a little. And now, let's look at the other carbon we were looking at. That's this one right here. Got a methyl group I'll call R. This whole thing here, not counting that carbon, is R prime, hydrogen, bromine, 4 different groups or atoms. Yes, hydrogen, bromine are R prime. They're different. And therefore, that, let me clean up this a little. This carbon would be chiral. Let's try another one. Oops. And here, let's look at this molecule. And if you look at the molecule in B, the same question, circle the chiral carbons. Now listen carefully. If a carbon is in a double bond or a triple bond, it can't be chiral. And if it has 2 or more of the same atom or group on it, it can't be chiral. So this is out. And now if we look at this carbon right here, it's double bond to oxygen, so that's out. If we look at these 2 carbons, they're in a double bond. They're out. If we look at this carbon, it's a carbon double bond to oxygen. That can't be chiral. Therefore, the only 2 to think about are this carbon and this carbon, because the rest can't be chiral. If it's in a double bond, or if it has 2 or more of the same atom, it can't be chiral. And therefore, what are the chiral carbons? Well, if we look at this one, chlorine, hydrogen, this I'll call R. This whole thing I'll call R prime. 1, 2, 3, 4 different groups or atoms or combination. This is a chiral carbon. But we're not done. Now, if we look at this carbon right here, it's got a hydrogen, a thiol group. This aldehyde, I'll call R, and all the rest of this R prime. 4 different groups or atoms or combination. 1, 2, 3, 4. Therefore, that's a chiral carbon. And that's how you do it. So I'm going to let you try 1 or 2 of them. And here's one for you to try. Your turn. Circle the chiral carbons. 3 points each. While you're doing that, I'm going to do a quick check of something. I see someone came a little late. like the only one. Hey, Jordan, don't tell anybody, but it's just you and me today, right now. I don't know, everybody taking the test when they shouldn't. Hi, Jordan. It's just you and me, but I was recording for the video in case people decided to take the test now and they can watch the video later. All right, let me go back and talk about what we're talking about. We're talking about chiral carbons. A chiral carbon is a carbon that has 4 different atoms, 4 different groups, or a combination of 4 different atoms or groups. Now, if you have 2 or more hydrogens on a carbon, it can't be chiral. Again, if you have 2 or more carbons, 2 or more hydrogens on a carbon, it can't be chiral. If the carbon is in a double bond or triple bond, it can't be chiral. So if we look at A, this is out, 3 hydrogens, this is out 2, this is out 3. This has a hydrogen, bromine, methyl, this whole thing, 4 different groups. That's a chiral carbon. Hi, Boris. And over here, hydrogen, hydroxyl, methyl, and this whole thing, 4 different groups in our atoms. And that's why they're circled. And we're doing C now. And the question is, circle the chiral carbons in C. And I'm also going to give you a D. Now, this is called a Fisher projection. In every intersection of a line, like here, here, and here, are carbons. And why don't you also on that one try circle the chiral carbons, 3 points each. For those who came in late, I talked about tomorrow, I'll go through the fats and oils problem set. And Thursday, I'll go through the carbohydrate problem set because I'll finish that. And I'm not sure if I'll get and finish the test so I can go over it tomorrow or Thursday. But one of those for sure for Thursday, I'll go through it. But it matters since I've been up since about 4:30, how late do I stay up and not make mistakes? When you're done, give me a thumbs up. Or if you want me to go ahead, give me a thumbs up. Thank you, Jordan. All right, let's go ahead. How do you circle? What is a chiral carbon circle? A carbon with 4 different groups, 4 different atoms, or a combination of 4 different groups or atoms. If it has 2 or more of the same atom, or if it's in a double or triple bond, it can't be chiral. That's out, because it's got 2 hydrogen. Here it has 3, and that's out. It's in a triple bond, so is that. That's out, it's in a double bond. And this one's out. So we have this one, and this one to consider. And if we look at this one first, hydrogen, iodine, methyl, and then all this is an R. Well, that's 4 different groups. So that gets circled. Now, if we look at this one right here, it's got a hydrogen, methyl, these 3 carbons with an iodine, and these 1, 2, 3, 4, 5 with a double bond, triple bond, and alcohol. So I can call this R prime methyl hydrogen. That's 4 different groups. So I'll circle that. Are we done? No, we have one more to do. And that's this carbon. Hydrogen, hydroxyl, these 4 carbons, and these 4 carbons, which are actually 5 carbons, counting the methyl, and then it's got an iodine. So this would be R prime, hydroxyl group, hydrogen, 4 different groups. And that's what we'd circle. Now, let's look at D. Well, if a carbon is in a double bond, it can't be chiral, so this carbon's out. If it's got 2 or more hydrogens, it's out. This one's out. Now, let's look at this one because Dr. White got sneaky. Notice it has 2 methyl groups on there. Both methyl groups are out because they have 2 or more hydrogens, but this carbon has 2 methyl groups, so it would be out. And that leaves us with this 2 carbons. And let's look at this one, hydroxyl group, hydrogen, aldehyde, and these 3 carbons, actually more, 1, 2, 3, 4, 5 carbons. So this would be chiral. If we look at this carbon, hydrogen, hydroxyl, this group here, and this group here, which is different, that would be 4 different groups or atoms, and that would be chiral. And you should know how to play that fun game, circle the chiral carbon. Now, turning the switch, click off right now. There's something called stereoisomerism. Isomers, as you remember, are molecules that have the same number and type of atoms, but they differ the way they're connected. Now, these stereoisomers have the same molecular and structural formula, but differ in the orientation and space. Just like if you look at the models I have here, these are stereoisomers. They both, let's say this is a carbon, it's got a silver, black, yellow, red. Silver, black, yellow, red. But they're not the same. They're not superimposable. Therefore, these are stereoisomers, and we have a name for those, and I'll talk about that right now. Now, I'll never ask on a test, what's a stereoisomer? And major features for stereoisomer, and I won't ask this, it's got to be a chiral center, it's got to be a rigid structural rigidity, which means carbon atom for this class. Now, switch is on, click. Let me get to my red pen. And you should know what an enantiomer is. Enantiomers, which I'll never ask the definition, but you should know how to identify or draw enantiomers, are molecules with non-superimposable mirror images. So if I were to ask, if I could spell, and as soon as you see draw the enantiomer, what I'm really saying is draw the mirror image. And how do you do that? Let's draw the enantiomer of glucose. Now, what I do, and you don't have to, is I like putting in my mirror. And the backbone, you're still going to see. Now, this is an achiral carbon, so you don't have to write it like this if you don't want to, because it's achiral. And what I normally do, being a lazy organic chemist, say, nah, I don't have to write the mirror image, because that's achiral. Remember, this is an aldehyde, which in the past I drew this way, but for sugars, my software does that way. Now, down here, you got two hydrogens, so that's achiral. You don't have to worry about the mirror image there. But the rest of the carbons are. So if you take and put your hand to the mirror, if I took my hand and put it to a mirror, what am I going to see in the reflection first? What's ever closest to the mirror. If I do this, I'm going to see this. If I went like this, I'd see the back of my hand, not the ring, because I only have a ring on one hand. But anyways, so let's take a look how to do that. All right, if you look at the first carbon with the hydroxyl group, this one, what's closest to the mirror? OH. What's farthest away? Hydrogen. So that's what you'll see in the reflection. Next one, what's closest to the mirror? OH. What's farthest away? Hydrogen. Now let's go to this one. What's closest to the mirror? Hydrogen. What's farthest away? Hydroxyl. And finally, the last of these four carbons, this hydroxyl is closest to the mirror. So we'll see that first, the hydrogen. And this is the enantiomer. Of glucose. I think you would like to have some fun doing the same thing. And I'll give you two of them. Let's make it a 2 for Tuesday. And why don't you draw the enantiomers of those, both of those products? 3 points each. Mirror image. And when you're done, give me a thumbs up. Thank you, Jordan. Thank you, Boris. All right, let's get to work. How do you draw the enantiomer of A? You don't have to do this, but I like to put my mirror in. And here's my backbone. At the top, I have an aldehyde that's achiral, so I can write that. This is an achiral, 2 hydrogens. Now, this first one, what's close to the mirror? Hydroxyl group. What's farthest away? Hydrogen. This next one, what's close to the mirror? Hydrogen. What's farthest away? Hydroxyl group. And that's how you do it. Oh, let's try B now. Here's my mirror. I have the 4 carbons here. Top, I still have an aldehyde, so I'll write it like that. This is CH2OH. It's an achiral, so I don't have to worry about the mirror. And now let's look at this hydrogen. It's close to the mirror. What's farthest away on that carbon? Right here, the hydroxyl group. Next carbon, hydroxyl group is closest, farthest away is hydrogen. And here we have what's closest, hydroxyl group. What's farthest away, well, I threw in a ringer, a methyl group. And finally, what's close to the mirror here, hydroxyl. What's farthest away, hydrogen. And that's how you would draw the enantiomer of this molecule right here, 3 points each. Now, switches off, but we also have a term called diastereomer. Those are stereoisomers that are not mirror images of each other. An example of that, which I didn't teach you when we learned about cis and trans, are diastereomers. Again, switch was off, click for that slide. Now, Fisher projection, which I won't ask on a test, but you'll see it in this class, you should understand. And a Fisher projection is like you have a 3-dimensional carbon. This dark wedge means it's coming towards you. The dashed wedge coming back away from the plane of the screen, and A and D are in the plane. And if you think of E, hold on, let's see if I can do this. One second, I'm working out my model so it works for you. Bingo. All right, notice this is coming towards you. This is far away, and this is in a plane like this. And if I were to take this and rotate it like this, and then flatten it out, which I'm not going to do, I'll ruin them, you'd have a cross and the different elements at the end of the line. Well, that's what a Fisher projection does. Notice I've rotated it and then smashed it. And when you rotate it, C will be on this side, E will be here on this part, and A is on the top, D is on the center. Now, you still have the stereochemistry, and you have to know these two right here are coming out at you. I used to put this on a test. I don't anymore, but you may need it for other classes. And these two are going back behind the paper. So even though you don't see it, this shows 3 dimensions in 2. And that's the beauty of Fisher projections. Now, let's look at chirality. If you look at this, this is glucose. These carbons are chiral. And I'll go real quick on this. The last hydroxyl group of a chiral carbon, this is not the highest, and this is C5. This would be 1. If it's on the right, it's called D. If it's on the left, it's called L. And you can get D-glucose, which is the major sugar in our blood. Now, I'm going to skip through this real quick. This won't be on test. If you have enantiomers, they're identical except for 2 things. They have the same physical properties like melting point, boiling point, but they differ in how they have what's called optical activity and reactivity with other chiral molecules. Now, optical activity, optically active compound rotates plane polarized light. Remember, light comes in at all waves around 360. Plane polarized light, just one wave, the rest are filtered out. And when you run that through an optically active compound, it will rotate it to the right or left, depending on the temperature, how many degrees. If you have a pure sample, it's always the same, just like a melting point. Well, one type of enantiomer will do something and the other will be different. And you can measure that. And I'm going to skip this about dextrorotary, which rotates plane polarized light to the right. Use a plus sign in the name. Lavatory or rotates it to the left, and you have a minus sign. All right, let's go through some stuff. And this is going to be click, the switch is off. Will it be on test? Now we have monosaccharides that are aldehydes, and we call those aldoses. And here's glucose. Again, this is as if you never need it later on in another course. Well, you heard it from Dr. White first. Now, if you have a ketone, and remember, this carbon here is bonded to carbons here and here. So it's a ketone. And this is called a ketosis. And I haven't worked on the sugar chemistry, why they came up with these names. But has anybody here heard of a very serious problem diabetics have called ketosis? And that's due to certain sugars in your blood that you can't get rid of. This is fructose. And again, a sugar, I won't ask that on test, is a mono or disaccharide. Now, here I have D-glucose, and it's in equilibrium with its cyclic form. Now, this type of ring and showing stereochemistry, which it does, has a name. It's called the Hawthorne Projection. And when I first started teaching this, I tried to get students to learn that. You could spend a week or so, put it on test. Nobody got it right. So I decided, you know something, these aren't going to be sugar chemists or carbohydrate chemists, so I'm not going to put Hawthorne projections on the test. But glucose can form this cyclic form, and we'll talk about that in a little while. And one thing, and D-glucose is the most abundant sugar in nature. Why? That's the sugar in your blood. Switches off, and turns out it rotates plane polarized light to the right. Now, this is fructose, and it's a ketone, so it's called a ketohexose, 6 carbons, and it's the sweetest sugar available in nature, and it's found in corn syrup. A number of years ago, 15, 20, maybe longer, chemists, not me personally, found a way to make high fructose corn syrup. And that means corn syrup, which comes from corn, has mostly fructose in it. And if you look at things like pop or other foods, guess what? To make it inexpensive and sweet, so you want to buy it, you've been conditioned sweet things are good for you, even though they're not always. And what they did was they took out table sugar, sucrose from a lot of things and replaced it with fructose. Why? Well, since it's a lot sweeter, you can use less than table sugar. Since it's less expensive, you save money. So if you look at things like pop, oh, let's do that. All right, let's see if you can see it. You should be able to. Does everybody see? Oh, let me get this out of the way. Ingredients right here in the middle of Coca-Cola. Can you see that, Jordan and Boris? Give me a thumbs up if you can. Ah, thank you, Boris. Have you noticed carbonated water? And what's the second thing? High fructose corn syrup. And that's in there to sweeten it. And it's pretty sweet. A lot of pops are that way. And a lot of foods that are sweet have high fructose corn syrup in it. Let's see if I can find some real quick. Any of your fast foods, breakfast cereals, sweetened things like yogurts, candies, soups and fruits, and obviously I just went through soft drinks. And those all have it. And that's there to make you want to like it because you've been conditioned. If it's sweet, it must be good for you. And I think at one point, even in baby food, they put in high fructose corn syrup. I don't know if they do that anymore. And fructose can be in a cyclic form too. And like I said, I'm going to skip Hawthorne projection. You know something? Normally I'd go another 5.5 minutes, but this is going to be a long topic to cover. So let's take a break now. It's now come back at 2:50. Let's take a 5-minute break and come back at 2:50. I'll see you then. I can get up and stretch. let's get going, boys. We're the only two here, so I can say that. Don't tell anybody I said that. All right, let's get going. Now, as I promised, no new reactions, so let's review some reaction that you learned for test number 2. And that reaction was if you took an aldehyde or ketone plus an alcohol in the presence of acid, keep your eye on the carbonyl carbon, what's attached to it stays attached. And then you get a hydroxyl group on this carbon, then oxygen and R from the alcohol. Now, let's take a look at the following. Here is glucose. And on the top here, you have an aldehyde. And this carbon right here, which is C5, this is 1, 2, 3, 4, 5. And this is a hydroxyl group on that carbon. This hydroxyl group on this carbon is this alcohol. And what happens is there's an equilibrium. Now, one thing I haven't taught you, I'll mention right now, and that is when you have the same two or more of the same, or two functional groups that are going to react in the same molecule, we call that intramolecular. Intra means inside the same molecule. Now, when they're in different molecules like this reaction, that's inter, like international, going somewhere outside the United States. And turns out when it's in the same molecule, intra, at the bottom right here, it goes real quick and you don't need a catalyst. When it's not in the same molecule, it goes slow. To help speed it up, we use a catalyst H+. Now, let's look at the top one in a little more detail. This oxygen comes here, bonds to this carbon, uses a hydrogen, it goes on this oxygen, and that's what happens. Well, if this oxygen attacks this, like up here, let's look what happens. Now, what's not involved in the reaction will not change. So immediately I can write the backbone, hydrogen, OH, H, H, hydroxyl, hydroxyl, hydrogen. Those won't change. Now my carbonyl, which is this up here, I'll still have a hydrogen on there, but notice I'll have a hydroxyl group. And then this oxygen is this oxygen, becomes this oxygen bonds to that carbon. So what does that mean? This carbon is bonded to, or this oxygen is bonded to this carbon. And this is what I call the cyclic form of glucose. And there's a name for it sugar chemists have that eludes me right now. And if this didn't happen, this is the first step Mother Nature uses to make all the starches and some disaccharide, 2 sugars. If this didn't happen, nothing, you wouldn't have that. Time to be subtle. Hint, know this. And you should be able to, on a test, if I give you this plus the equilibrium, you should be able to give me this product. If I give you this product and the equilibrium, you should be able to go backwards to that starting material. And again, let's go through it. It's the same general reaction right here, ketone or aldehyde, and the aldehyde and glucose is this carbon plus an alcohol. The alcohol is on C5, this hydroxyl group. The red line shows that it tacks, and this is where it forms a single oxygen carbon bond, this one right here. Now, years ago, students couldn't do the Hawthorne. I came up with the ugliest, but easy to use way to draw that ring system. And that's how you should do it, like I did here. And again, hydroxyl group tacks this carbon, just like up here, and forms this bond, which is this bond. Now, just so happens, R and R prime are in the ring connect together here in the backbone. And you should know how to do this. Go back and watch the video again if you need to. And I'm going to do this again tomorrow because it's so important. Now, this is for glucose. Now, another important sugar in our daily life, which I just talked about, but let's take a look at it again. Is fructose. And fructose has this structure. It has a carbonyl, not at the end, so it's a ketone. I'm cheating because I always forget the structure of fructose. You don't need to know it for a test, but and let me just check that I did it right. Excuse me. And the answer is I did. All right, now, same thing happens, same reaction. Ketone or aldehyde, in this case, it's a ketone plus an alcohol, acid catalyst. This attacks that. Here's my carbonyl carbon. What's attached to it is still attached, OH, and then from the alcohol, OR. And here's that carbon. Well, in here, it's this carbon. And because it's intramolecular, you don't need a catalyst. That's why it's in equilibrium. And let's take a look at colored pen. This hydroxyl group is this hydroxyl group. It attacks the carbonyl, so this will attack the carbonyl. And this always, for both of them, happens on carbon 5. 1, 2, 3, 4, 5. And what isn't involved in the reaction does not change. Now this is this carbon right here. And notice it will be this carbon right here. So it has a hydroxyl group and it's bonded to the oxygen that's on this carbon. And that's how you draw that ring. And that's why I took the break earlier, because this is long, a lot of stuff. And once again, you should know this also. This is fructose. And it also will react with this reaction to form this hemiketal. And I think that's called a fructoside or something like that. Don't quote me on it. And you should know, if I give you fructose, the structure, this equilibrium, you should be able to develop this structure, the product. If I give you the product, you should be able to work back to the structure of fructose. And I'll go through this again tomorrow, because it's a hard one, and I'll do it tomorrow a couple more times. And can I have a show? I'll phrase this way. Here's the cyclic form using a Hawthorne structure. And here's the way I do it, my real ugly carbon-oxygen single bond. Which is easier? If you think my way is easier, writing it this way, as opposed to learning how to draw it this way, give me a thumbs up. If my way is easier than learning how to draw the ring this way, give me a thumbs up, or don't vote. Got this way or this way, which is easier to draw? Well, it looks like nobody wants to vote, so I will. I think this way is. And when I started having students learn this way, on test 4, scores went up. All right, like I said, I'm going to come back to this tomorrow. We'll do it once or twice tomorrow. Let's do it again here. If we start out with glucose, here's my carbonyl. Hold on one second. Here's my carbonyl, this right here. The alcohol, which attacks the carbonyl, is this alcohol right here. Attacks that, and it opens it up to this right here. This carbon right here, which is this carbon right here, will have a hydroxyl group, hydrogen, bond right here, which is this right here, and the rest of that is my R prime and R double prime. And with a fructose molecule, instead of having an aldehyde, the carbonyl is right here. And again, same reaction, alcohol attacks the carbonyl carbon, which is this right here. It's always this alcohol on carbon 5, C5, and it attacks, and you form a carbon-oxygen bond, this right here, which is this bond right here. And on there, there'll be a hydroxyl group. And what is connected to these carbons and these carbons are part of your R prime and R double prime, which make up this ring. And that's how you do it. And if I give you fructose, the structure, you should know how to draw the cyclic form. If I give you glucose, you should know how to draw the cyclic form. If I give you the product, the cyclic form here, you should be able to get back to glucose. And if I give you the cyclic form here, you should be able to get back to fructose. And that's because this is very important. And I went through this. Now, let's do real quick reductions. Now, for test number 2, you learn the following. Well, let me get rid of the blue. Let's get a fresh page. And if you have a catalyst, nickel, platinum, or palladium, hydrogen, you have a pi bond, and you can break that pi bond. And each atom of the double bond gets a hydrogen. Guess what? You can do that with glucose. I'm going to let you try this on your own. Hint, if you don't know a reaction with a functional group, guess what? For this class, it's not going to react. So will an alcohol and OH group react with nickel and a catalyst? And the answer is no. So go ahead and try that reaction. What would be the product or products of that reaction? 3 points each. Hi, Jimmy. You're done. Boris too, and Jordan just joined us. All right, let's do this one. Question is, what's the reaction? And here's the general reaction you learn for test 2. Well, I've got an aldehyde here. The rest of the molecule, nothing's going to change because it will not react with hydrogen and catalyst. So I can redraw this. And what will happen here? This, which I can also redraw like this. And these molecules are the same. I just put the 2 hydrogens on there, and the hydroxyl group I wrote a little differently. This new molecule has a name, common name, or is it a trade name? It's called sorbitol. Now let's take a look at sorbitol. And one of the things I've been doing more and more, as you notice, is asking, why are we learning this stuff? And the obvious reason is you want to get a good grade in my class. so you can get into school or program that told you to take organic. But really, why are you learning this stuff? Let's find out. If you look at sorbitol on Wikipedia, here's the molecule. And you've got each benzyl line is a carbon, 1, 2, 3, 4, 5, 6, and each carbon has a hydroxyl group, which is what we just showed. Now, what's sorbitol? Well, it's a sugar alcohol. It's something that tastes sweet, but your body doesn't metabolize it quickly. And it's made by the reduction of glucose. And what that means is you react it with hydrogen and a catalyst. And this is found in a lot of the over-the-counter drugs or other remedies you can buy to make it sweeter, but at the same time not give it calories. They put this in here. Also, it's in natural foods like apples, pears, peaches, and prunes. Oh, that's why I like it. Dr. White loves his prunes. Oh, I love them. My father's mother, Grandma White, got me hooked on prunes when I was about 4.5, 5. She loved them. And that's how you make it. All right. Now, this slide probably doesn't make sense to you, but I'm going to explain it. And that's the glucose side is the acetal or ketal form from a cyclic monosaccharide. And the glucose side is the glycoside form from glucose. And remember the reaction with methanol. Well, the top two, I'm not going to worry about, but the third bullet, remember the reaction with methanol, that's for me, and I do. So let's look at something. Now, I promised no new reactions, but this is going to be a wrinkle on a past reaction that you learned for test 2. Switch is on. If you take a ketone or aldehyde, react with 2 molecules or moles of an alcohol, acid catalyst, you'll get this acetal or ketal. Now, what I didn't show you was it's stepwise. And this will not be on test, but it'll help you understand what I will show you. And if you take an alcohol and acid, you learned this for test number 1 or number 2, you will get this compound, the hemiacetal or hemiketal. And stepwise, the second alcohol reacts with the hemiacetal or hemiketal to take that and replace it with this. If you notice on both oxygens, you have the same R group. It's symmetrical. However, and this is what I'm going to teach you that's new, if you take this alcohol, this hemiacetal, hemiketal, and react it with a different alcohol and acid, you make this first isolated and then do the second reaction. Well, the same thing happens. I'm going to replace that, but instead of with OR, I'm going to replace it with R triple prime O. And what you get here's this carbon with this on there. This was on there. And this hydroxy group is now replaced not with OR, but with OR triple prime. And this is an unsymmetrical. R and R triple prime are not the same on the different oxygens, where they are up here, where this is symmetrical. So what? Well, this second new reaction is the basis to help make all starches in our life. So first of all, let's look at a reaction like this. Now, we look at this reaction up here, and really we're just looking at this reaction. This carbon here is this carbon here. This hydroxyl group here is on this one with the other oxygen right here. And if I react this with alcohol and acid, I'll replace this like I'm replacing this. So let's do it. What's not involved in the reaction doesn't change. That doesn't change. The only thing that changes is this becomes OR triple prime. And because of that, I'm going to let you try this one. What would be the product or product reacting this with methanol, CH3OH, and acid? And hint, look above here. Now you can see both reactions. This I'll never give as a synthesis, but you should know how to do this to do the product or products for this reaction. When you're done, give me a thumbs up. Thank you, Boris. Thank you, Jordan. And everybody's done, so I better get to work. And what do we have here? This right here, the hemiacetal form of glucose. We're reacting, what's this? This alcohol. What's our triple prime? This right here. Oops, I wonder why that's Give me 1 second to do something real quick or real slow. Hopefully that helped out. We'll find out. No. All right, let's try this again. So that's our R triple prime. What's here in the molecule that's not involved in the reaction stays the same. Don't forget this bond. Don't lose it. And this hydroxyl group is this becomes OR triple prime. And what's R triple prime? Methyl. And that's why I said, remember methyl. Oh, let's do this then. All right, I've got to close this. Hang on. All right, let's do this again. There we go. All right. Sorry about that. Remember what's not involved in the reaction, you just rewrite, which is what I'm doing now. And that's what we got. Now let's try another one. I'll give you one more. And why don't you try this one, gentlemen? I don't know where all the ladies went today, but they're not here. Oh no. But anyways, what would be the product or products for the following reaction? Let me help you out a little. There. Thank you, Boris. Thank you, Jimmy. All right, let's get moving because we got stuff to finish today. And what do we have here? A hemiacetal of glucose, which is this. When you react it with an alcohol and acid, the only thing you change is the hydroxy group to OR triple prime. Oh, we've got an alcohol here, and this is my R triple prime. And whatever is not involved in the reaction, I can just rewrite. So I will. And this OH becomes OR triple prime. The carbon with the hydroxyl group will be the carbon on the oxygen here. And that's how you do it. Now, one of the questions you should ask is, why? Why? What's so important, Dr. White? And that's a good question. Now, let's take a look at something I'm going to do on the whiteboard. Do not write this down. If I were in a classroom, I'd be telling you, don't write this down. You can always come back to the video, but in the classroom, you couldn't. All right, give me a couple minutes because I've got a lot of work to do. Oh, I'm going to try something. Let's see if I can pull this off. This will be the first time I ever did something like this. not erase the board, but watch what I'm going to try and do. Whoa, that's not what I want to do. I see what I did wrong. Huh. All right. All right. Let's see if this will work. I'm wasting too much time. Sorry, gentlemen. Back to the old-fashioned way. I'll have to figure this out on my own another time. I promise I'll get done before midnight. uh, all right. If you notice, I have this for the same molecule, the cyclic form of glucose. Now, as you learned right here, an hydroxyl group on that carbon reacting with an alcohol, you'll form this oxygen R to the oxygen that's bonded to this carbon. Well, if we look down here, I have this carbon. Here's my alcohol. Here's the hydroxyl group. What happens? You lose this, and this is bonded here. Now, if we look at this molecule right here, I have that same setup. Hydroxyl group on the carbon of the acetal, hemiacetal, this hydroxyl group. Guess what? This alcohol will do the following. And if I look at this molecule, same thing. Hemiacetal with a hydroxyl group. This next glucose has this alcohol. And guess what that can do? This gets lost or eliminated. Oops. And this bonds to that. And if I look here, I can do it again and again and again, like the Energizer Bunny. What this really is glucose molecules bond together in an acetal linkage, because you form the acetal. And What do we call this when you link a lot of glucose together like this? Starch. And this is how the good things like potatoes, French fries, potato chips, or rice, the starch is formed by this reaction that Mother Nature does. So what I could say, and you should know this, I take a lot of glucose molecules and react them with a lot more glucose molecules in the presence of an acid we call an enzyme. Enzymes, a lot of them are acid catalysts. You will make starch. And think about it. All the starch you know in your life, the good stuff, is made from this reaction. Now, what holds the starch molecules together? An acetal linkage. And what did you learn from test 2? If you take I'm going to go a couple minutes into this next break. I'll still give you a 5-minute break. I need it too, but let's finish this up right here and then we'll come back to some other stuff. If you take an acetal or ketal, acid and water, you get back the aldehyde or the ketone you would have used to make that, plus the alcohol you would have used to make that. Now I have a 2 there, you don't need it. Now, if you have starch, which is this, and you add acid like in your stomach and water, what do you get back? Well, you get back the molecule, which these are connected together, and we call that glucose. And that's why glucose is the most abundant sugar in nature. It's the sugar in your blood because your body breaks down starch to make glucose. And what you're breaking down are these linkages right there, and you get back glucose. And this you should know. Take starch, react with acid and water, you get glucose. And I promise let's see how much time let's take a break right now. It's 3:41, come back at about 3:46 and we'll continue. I'll see you in 5. Be back in 5. Sorry about the late start. It's been a rough day for Dr. White. Oops, I shouldn't have said that, but it has. All right, let's get back to where we were. We're talking about how if you eat starch, because of the acetal linkages between the glucose molecules, you get back glucose. Now, you should know, hint. Oh, I better write it in red so you're. You should know how to describe. Oh, I forgot to do this. We're back. You should know how to describe with both words and a general reaction what happens when you eat a carbohydrate. And what's in your stomach? Acid and water. So it's acid hydrolysis. Of, and what's the functional group that holds together glucose? And the answer is an acetal. This right here, each one of these, it even says it on there, is an acetal linkage. And therefore, you have acid hydrolysis of an acetal. You should know how to describe when you eat a carbohydrate with words, acid hydrolysis of an acetal. And the general reaction, which you learned for test number 2, acetal or ketal, acid and water. And what do you get back? The aldehyde or ketone you would have used to make that acetal, plus the alcohol you would have used. And turns out this alcohol is connected to here in glucose, but you don't have to put that down. So you should know when you eat a carbohydrate, how to describe it with words and a general reaction, and that's acid hydrolysis of an acetal. And here's the general reaction, which you learned for test 2, and you should know that on a test. If I ask, describe with words and a general reaction, what happens in your stomach when you eat a carbohydrate, it's acid hydrolysis of an acetal. That's the functional group holding glucose together. And you should be able to write this general reaction. Now, yes, earlier in the week, I talked about, you should also know, and we mentioned, I talked about this, when you eat a fat, something with fat in it, or oil, how to describe what is happening in your stomach with words and a general reaction. What functional group is in a fat or oil? And the answer is an ester. Therefore, this is acid hydrolysis of an ester. And hopefully for test number 3, you learn ester, acid and water, and you get back the carboxylic acid plus the alcohol you would have used to make that ester. So when you eat a fat or oil, you should be able to describe with words and a general reaction, functional group in a fat or oil is ester, in your stomach, acid and water. So it's acid hydrolysis of an ester. And the general reaction, which you learned for test 3, ester, acid, water gives you here a carboxylic acid and an alcohol. And as you just learned, when you eat a carbohydrate, what happens? You have acid hydrolysis in the functional group that holds together glucose molecules in a carbohydrate. Starch is an acetal. So it's acid hydrolysis of an acetal. Here we have an acetal ketal, acid water. You get back the aldehyde or ketone plus the alcohol you would have used to make that. And those are things you should know leaving my class. Now, if I look at the clock and how we're doing, I'm going to do something different. I've been pushing you guys real hard all semester. We're just a little bit ahead, so we can start right now, the lab. It's time for today's lab. I had to do that. I needed to pick me up, and it did. But before we do that, I have to open it. All right. Does everybody see the polymers lab on the screen? Uh-oh, I better check. Yep, you should see it. You see that? Thank you, Jimmy. All right, let's talk about polymers. And polymers are very large molecules that play an important role in our daily life. The word polymer comes from poly, meaning many, mer, units. And what they are these large molecules, I mean large, that have repeating units. Think of a railroad freight train where you have boxcars over and over again, like thousands or millions of them. Well, that's a polymer. Now, there are a couple of polymers I like to teach you about in this lab. And Dr. White's sad because we do this to have fun in the lab, but I made a decision more people could take this class if I did it internet than if we did it face-to-face this summer. And I think that's a good thing. Now, when you have, and this is a new functional group, an isocyanate reacting with an alcohol, you form this new functional group, a urethane, and they're quite stable. Now, if you have a molecule with more than one isocyanate in it, and another molecule with more than one alcohol, you'll get a polymer where this keeps on repeating. And we call that a polyurethane, poly, many, urethane, and it's a polymer. Now, there are two types of what we call urethane foam. And when you make this reaction, it gives off heat. And because of that, if you have a very low boiling liquid in there, it will expand and you'll get bubbles or a foam. How many of you ever seen foam like on top of beer or anything? That's bubbles surrounded by chemical liquid, the beer. And there's CO2, but we use other things. Now that foam and urethane can be rigid like a 2x4 or flexible like your pillow. Or if you sit in your car, you're sitting on a seat that's got cushion, and that's a urethane foam. Now, the type of polyol and diisocyanate determines what kind of urethane foam you get, solid or liquid. I'm solid or liquid, flexible or rigid. Now, this is an area I know quite well because I've got about 4 US patents, I think 4 or 5, 4 in this area. I must know it well. Now, a lot of urethane, listen carefully, rigid urethane foam is used as an insulator, insulation. If you've ever seen pictures of guys spraying it in somebody's attic, that expands and solidifies, that's a very good insulator. It's rigid. Now, if you look at your refrigerator at home, it's got a thin wall between the inner box and the outside of the refrigerator. Now, if you go back and look at refrigerators from 1940s and 50s, it's pretty thick because back then they used glass wool and it needed real thickness to get the R value to keep the cold inside the inner box of your refrigerator. Now they use urethane foam, rigid foam, and it's a great insulator, so you don't need as much, and it's thinner. Now, in this industry, a lot of it's done on construction sites or in plants with people who don't have college degrees. So the urethane industry did a great thing. They came up with an idea to make it real simple for non-technical workers. And what they did was come up with what's called an A side and a B side. And you buy it and you mix the two together equal parts. Now, take notes. The A side is just the isocyanate. The B side contains the polyol. That's the alcohol with or molecule with more than one alcohol. So you get a polymer, and this is usually a polymeric isocyanate, a diisocyanate. Plus, this contains a catalyst. And usually this is a tertiary amine, like polycat 8 I showed you how to make in a lecture a while back. You also have what's called a blowing agent. And that's what makes the foam. And you usually have to make a good foam, usually have what's called a silicone surfactant. And I came up with some chemicals that help improve the B side. And I'll tell you a story in a second, I still remember. But anyways, you mix the two together and all of a sudden you'll see a color change. Now there's two important things to know. One is called the cream time. And that's when the reaction starts. And the cream time tells you when the reaction starts. And it looks like if you have black coffee and you pour cream into it, you know how it gets that lighter color brown or whatever. I'm not a coffee drinker, so you're asking the wrong person. Well, when you mix two together and it starts, it gets that lighter color. The isocyanate is usually a dark color. This is almost clear or light honey color. And when you mix two together, and you can affect the cream time by changing the catalyst. For a quicker cream time, a smaller cream time, that means faster, you add more catalyst. Now, there's another important thing that you measure, Tack free time. And that's when the foam is no longer sticky or tacky. In other words, if you're trying to get it out of a mold, because some they sell board stock they make in molds, and you want to know when to get it out, so you need the tack free time. What you do, if we were in the lab, I'd give you tongue depressors, and you touch the top of the foam until it's no longer tacky. And what we would do is in a plastic cup, you pour 10 grams of the A side, the isocyanate, 10 grams of the B side. And since urethane sticks to everything, it's hard to get off. We always do this in a hood with newspaper underneath. In fact, the last time two times we did it, underneath the newspaper, we even put plastic to be careful. You mix it, look for when it changed color, the cream time. Then because this is an exothermic reaction, the heat caused the blowing agent to expand, which makes the foam. And you record when it's no longer tacky. Now I give you the cream time tack-free. Was it exothermic? Yes. And what did it look like? But let's take a look at this in real life. Oh, time
Let
out.
this soft mineral melt in your mouth.
Talk about molding foam. Specifically today, we have a 3 pound per cubic foot molding foam that we want to discuss some of its attributes.
Quick question, gentlemen. Do you see the YouTube on your screen right now where he has A and B in front of him and on jugs? Thank you, Jimmy.
This material starts its life off as thin liquids. It's going to be mixed at a 1-to-1 volume measurement, and then it's going to expand. It's going to expand to form a very lightweight foam. And as we said, in this case, it's a 3 pound per cubic foot density foam. So it's going to expand 24 times its liquid volume to create a lightweight, non-absorbing, closed cell foam that can be easily sanded or carved to dimensional shape. It can be cast as backups or as freestanding forms. It can be painted with automotive paint and used in conjunction with fiberglass resins. In conjunction, it can be used for flotation. It has an extremely good compressive strength. This particular 3 pound foam has 40 pounds per square inch compressive strength, so it'll support a human walking on it. But also it's good down to depths of about 300 foot in the water. To demonstrate how this liquid foam is going to actually be mixed and used, we first conditioned our liquids to 72 degrees Fahrenheit. Best temperature to be at. Hotter means faster reaction. Colder means a slower reaction is going to create higher density foam than desired. We're going to measure out equal portions in liquid. In this case, we've had some pre-marked beakers. We measure out part B, and now we're going to measure out part A.
That's the isocyanate.
And then we're going to take a flat spatula, not a round dowel, and we're going to pour one into the other, and we're going to simply mix. And it's important that you quickly scrape the sides and the bottom of the container to incorporate all the A and the B so that they get fully reacted.
You see how that changed color and became white? See how it's not? It looks sort of like coffee. And as these starch mixed
Incorporate all the A and the B so that they get fully reacted.
See how it's color lighter? That's the cream time. It's fast. And don't ignore what he said about temperature. Catalyst is the way you change things.
Doesn't take much. When the material starts to react, it'll form a nice even cream color, and you need to pour that into your mold. For this demonstration, we're just going to do a free rise block of foam so that you can actually see how this material expands. We'll pretty well got it mixed, and it's going to create just a little bit of heat on its own. Again, 72 degrees is the perfect temperature to start mixing at. It gives you about a minute or so of time to actually mix the foam and pour it into the mold. You got to be careful now not to put too much foam into a closed cavity mold, because it does create quite a bit of pressure on its own, and it could warp your mold. So now it's starting to come up. And actually, to demonstrate this, we're just going to let it come up to kind of show you what we call free rise in this. So it comes out, it's going to expand, and within about 2 or 3 minutes, it's going to get to full hardness. And we'll be able to actually pick this up, carve it, and show you how it's used. It's best not to get this on your hands, and I'm not wearing gloves, but you should wear gloves with this right now. because it loves to stick to human hands. That's about it. And you can see I only had about 500 milliliters of liquid, but you can get a sense of how much volume with this. Now, it's been about 5 minutes since we initially mixed our foam, and you can see it's pretty well set. It doesn't stick to polyethylene or propylene plastics, so common garbage bags work quite well as a barrier. As you can see, it's durable, and it's fairly lightweight. And as we mentioned,
Now, the one we do in the lab, we don't let it go over the cup. No, it fills up and fills in. It's really nice. And in a couple minutes, it's just, we use a higher density. I have a formulation for that. And it's as hard as wood, that hard. And it's really neat to do. All right, let's move on with the lab. And let's talk about the next one. And this is nylon. Nylon is a polyamide. Remember, this is an amide. Now, what I showed you was with a carboxylic acid and an amine, you make an amide. Now, in real life, acid chloride is much more reactive than a carboxylic acid with amines to make amides. But because this gives off HCl, we have base present. And you have a diacid chloride, 2 of them, and a diamine, and you'll get a polymer where this repeats all over and over again. And here, the way we do it, if we were in the lab, you take a beaker with label A, another beaker label B. In beaker A, you put solvent dichloromethane, then you add the acid chloride, which is acetyl chloride. In beaker B, you put some water and you add the diamine, hexane diamine, and you also add a little base because that sodium hydroxide will scavenge and neutralize the HCl you make in this reaction. You don't want that reacting with your amine. Then you carefully on the side pour beaker B into beaker A. And when you do that, carefully afterward, I think it's B is on top and A is on the bottom, and you'll have this interface. And because you've got water and diethylene dichloromethane, polar and nonpolar, they don't mix. But if you take a hook, a wire, and pull it up, you'll pull up this white solid, which is your nylon. You keep on doing that. I've had people do it for about 5 minutes. Now, let's watch this in real life. And again, this is one of those, I wish we were face to face, but we're not. But still, you'll get an idea, the feel for it.
Grammarly helps you work more efficiently.
I don't know about that, but I don't need a commercial.
Familiar mushroom clouds snake skyward, hurling the atom's deadly radiation high into the heavens.
I don't know why they have that.
Okay, this is the aqueous solution. I'm going to pour this in here. And that aqueous solution contains the acid, the diacid. And this is a solution of the hexane diamine. It's dissolved in hexane, and hexane is less dense than water. So this solution is going to float on top of the other one. And then where the two solutions come together, the interface between these two solutions is where this reaction is going to take place. How many fingers do I have? Anyway, here we go. Maybe these were gloves.
Obviously not used to putting on gloves.
Okay, so I'm very carefully going to pour this down the side, and then where the interface is, we'll have contact between the diacid and the diamino hexane. hexane layer is floating on the top here. But of course, where they come together is where the polymer can be made, where the condensation reaction is happening. So then I'm
Now,
gonna
he
reach in here
uses
and where
tweezers,
the interface
we
is, I'm
use
gonna
a
pull
hook.
some-
and see that white solid? That's nylon.
See how much nylon we can pull out.
And I have students wrap it around a
meter.
beaker. It's easier to do than the way he's doing it. And you keep on pulling it for a long time, like the Energizer Bunny. Because the two layers are reacting and at the interface, you're forming nylon.
I'm sure we're gonna beat that record today. Where are we at, 4?
And you can go on like this for a couple of minutes before you run out of making nylon.
Now you can see that you can get a lot of material out of a very small quantity. I only dissolved a few grams of.
And students, it's a lot of fun, but unfortunately, because of the pandemic and we're doing this online, you just have to watch it and get the feel for that. Now, remember, what's the functional group holding nylon together? It's an amide. The functional group holding nylon together, it's called a polyamide because the amide functional group. And those react like I've taught you. Now, part 3 is just a really fun reaction. And watch closely. If you take boric acid or sodium borax, 20-multene, and you react it with 3 alcohols, you'll get what's called a borate ester. And yes, I have 2 patents in borate esters, so I know this. Now, if you take an alcohol with more than 1 hydroxyl group, this will be a monster molecule. Now, what I have you do in this one is, in a clean beaker, put some of the alcohol, and then add a little water, and then add the boric acid solution. Now, in one, I have isopropanol or isopropyl alcohol. And that's your alcohol. The other one, we use polyvinyl alcohol, known as Elmer's glue. And N here is about 500,000 to 1 million, more closer to 1 million. Now, when you mix the 2 together, you get this reaction. And when you do it with the isopropyl alcohol, here, you get a clear liquid. When you do it with the polyvinyl alcohol, Elmer's glue, you get this gooey, slimy, fun, white solid. And let's take a look at that. Commercial time again.
Hey, boss. So I know you're looking to move your employees like.
Hi everyone, today I'm so excited to show you our favorite slime recipe. This is the most amazing, softest, gooey, oozy slime, and it's so much fun to play with. First, we will begin by creating our slime activator. You use 1 cup of hot water with half a teaspoon of borax.
Borax is the boric
Make sure
acid.
to stir it well so that you dissolve all the powder. Once you are done mixing, you can keep it to the side. If you prefer not to use the borax activator, you could also use contact lens solution that contains boric acid. Now we'll start our slime. I'm using 1 part of glue.
I have you weigh it out.
Palmer's PVA glue. And I'm going to mix it with warm water. So I'm going to add the warm water into the glue bottle.
We have a huge bottle, so you don't have to do
Now
this.
close the top, and I'm going to shake it. That will help spread the leftover glue inside. Then open it up and add it to your mixture. Now just go ahead and mix it all together so that you don't end up with any clumps. You want a nice smooth mixture.
We use tongue depressors, not wooden
I tend
kitchen
to keep on
spoons.
having a bunch of ice cream sticks because they're the easiest to clean up afterwards and they do a great job of mixing.
We use tongue depressors.
Then you will add your food color of choice. I choose to use food color
That's
just because I like
optional.
how vibrant the colors come out. You just need 1 drop. I'm going today with a purple, different slimes at home. So we've got a butter slime that's yellow. We have 2 fluffy slimes that are pink and blue. You can find the recipes and video tutorial. Get a good mix before you start adding it in. This is really important that you add it in really slowly because this is sort of the part that's going to make or break your slime. So I tend to go and add in a teaspoon at a time, and then I mix, and then I can add another teaspoon at a time and mix.
See how it's already getting gooey and ooey?
You'll see that it starts to sticking together. As I raise my spoon, I'll show you that. Yeah, see?
I'm gonna jump ahead.
It's really fluffy and so much fun to play with, but the only thing is teaspoons of borax. Adding between 5 to 7 teaspoons of borax. I probably added I think I added 6 teaspoons, and I could tell from the consistency with my hands that it was still a little bit too sticky. So I went ahead and added 1 more, mixed again, and then now you start kneading it.
And that's why I mean on the lab, gooey, slimy, white solid. And that's the polymer of this. And the reason it doesn't stay in water because of the molecular weight. The polyvinyl alcohol will bond with a lot of these to make monster molecules. The alcohol, which is not a polymer, not a polyol, only has 1 hydroxyl, and each R group would be isopropyl. So it's a tiny molecule. And that's why you see the different observations. Now, for this lab, here are the questions. And with that, I'm done for today. I'm gonna let you out a little early. Don't tell anybody, but I've been pushing you hard this semester. So you can take a little earlier. And with that, I'm done. Tomorrow, I will go through the fats and oils problem set, and I'll go back and repeat those reactions in the carbohydrates chapter. And I'll finish a little more interesting stuff with carbohydrates. And with that, I'm going to say, Gehen gesund, goodbye. I'll see you tomorrow. Bye now. And hopefully either tomorrow or Thursday, I'll have test number 3 graded, and we'll go through the answers. I'll cut that out of the video, but I'll also email you with your individual points. Bye now. Gehen gesund.